Good morning everyone. This is Dr. and Sri Ramya, Assistant Professor of Civil Engineering Department. Today's topic is laminar flow through circular pipe. So here we are deriving a laminar flow through circular pipe. So here are the assumptions. First assumption to derive a laminar flow is a steady state flow. Steady state flow. The flow should be in steady state. That means there is no change with time. Whatever the parameter we take, that should be, with respect to time, it should be equal to constant at 0. And second point is incompressible fluid. So here the fluid should be incompressible and also it should have a constant density in that fluid. And third point is fully developed laminar flow. Here the velocity varies only with the radius, not along the length of the pipe. When we take a circular pipe, the flow should be in x direction. The flow and the velocities should be same. But when we are taking in in this y direction, this is the x direction, and here is the y direction. So when we take a flow in x direction, there is no change in the velocity. When we are coming to in y direction, there we are seeing the change in velocity. We already in previous lecture we have discussed that laminar and turbulent flows, right? So in laminar flows, all the particles are moves in a straight line, right? And also we have talked about a velocity profile, velocity distribution in a closed pipe, right? So when we are seeing a laminar flow, the laminar flow velocity profile, velocity distribution is a parabola. At the boundaries, the velocity is 0, and at the center of the pipe, the velocity is maximum. The center of the pipe, the velocity is maximum. When we are seeing at the boundaries of the the flow at the boundaries, there the velocity is 0. This is also we discussed, that is due to the friction loss, right? So the velocities should only varies only in the radial direction and not in a length, along the length of the pipe. So and another one is no slip condition. So the no slip condition means there is friction is acting in that pipe. If there is a slip condition, the velocity profile is completely uniformly distributed throughout the diameter of the pipe. But this is for slip condition. This is for slip condition. In non-slip condition, as we have discussed, that the velocity profile is 0 at the boundaries and maximum at the center of the pipe. So this is no slip condition. This is no slip condition. We have the friction losses. That is boundary. And third one is axisymmetric flows. There is no variation in the circumferential direction. These are all the assumptions of the laminar flow through circular pipes. Circular pipe. Here, this is a circular pipe, and in that circular pipe, flow is moving from left to right. The flow is moving from left to right. And here, if you see, there is a small portion. That small is an element to derive a laminar flow. So we are taking a small element. The length of the small element is dx, and the length of the width of that small element is dy. In the lengthwise it is dx, and in diameter wise, in y direction it is dy. Small element. Now here we are calculating the forces which are acting on the small element. So here when we see here, four forces are acting on the small element. On the small element, there are four forces are acting. Here on left hand side and right hand side, there are pressure forces acting. And at the top and bottom of these elements, the shear forces are acting. From left to right, we are seeing the pressure forces, and here from up and down we are seeing shear forces, and at this here left to right it is pressure forces, right? So, and the small element diameter of the small element is dr, and this is the small radius of the small element is r, and the circumference is dr, and the complete pressure forces P1 P into pi r square, and here on the right hand side we are taking P into pi r square plus dou P by dou x into dx into pi r square, because these element complete from here to here we are taking differential pressure with respect to x, dou P by dou x into dx into pi r square. Here these are the pressure forces for left and right, and the shear forces upside is shear stress into pi r square into dx, and here the length of this complete from, and here one more thing, here we are observing two sections. One section is here and second section is here, right? Two sections we are taking. These two sections are taking to calculate the pressure drop, delta P. We are taking two sections, section 1 and section 2. The section 1 from left to section 1 distance is x1, and the distance from section 1 to section 2 is L, and the distance from left to the section 2 is x2. x2 is equal to L plus x1, right? So here we are seeing the forces. So shear stress. First of all, the shear stress. Shear stress is shear force by area, right? So we need shear force. Shear force is equal to shear stress into area. So that's what we are doing here. This is the shear force, and tau into 2 pi r into dx is the shear force, right? And here let P be the intensity of the pressure at left end and the intensity of pressure at the right end B. So here this is for pressure force at left side is P into 2 pi r into dx. This is for left side pressure force, and here for right side pressure force. This is right side pressure force. The left side is pressure into pi r square, 2 pi r into dx, and here coming to this right hand side, that is P plus dou P by dou x into dx whole to the power of pi r square. Alright, so here the shear force tau is equal to 2 pi r into dx on the surface of the fluid element. The pressure forces on the left hand side is 2 pi r square on the left hand side, and pressure forces 2 pi r square on the right hand side is P plus dou P by dou x into dx is on right hand side. So now we have already assumed that the flow in a circular pipe is moving in a steady state condition, right? In steady state condition means all the forces which are acting on the cylindrical element, that is should be equated to 0. That must be 0. So here is the pressure force on left side P r square, and here P plus dou P by dou x into dx pi r square is for pressure force at right side, and tau into 2 pi r into dx is shear force, that is equal to 0. So now I am equating to 0, and I got that tau is equal to minus dou P by dou x into d into r by 2. So I got tau is equal to minus dou P by dou x into r by 2. The above equation shows that flow will occur only if the pressure gradients exist in the direction of the flow. So from this equation, we are telling that the pressure gradient exists in the direction of the flow. And here also we are seeing the negative direction. So the negative sign is indicating that there is a decrease in the pressure force in the direction of the flow. That negative sign is indicating that there is a decrease in the pressure force when flow is moving in the direction of the flow in a pipe, in a circular pipe. So after getting a generalized equation, here is the shear stress varies linearly across the section. It is varying linearly across the section. Its value is 0 at the center. The value is 0 at the center and maximum at the walls. Shear is maximum at these walls, and minimum completely 0 is a minimum at the center of the pipe. And here the velocity gradient we discussed, right? So velocity is 0 at the boundaries and velocity is maximum at the center. It is maximum velocity. So we got a generalized equation that tau is equal to minus dou p by dou x into r by 2. This is a generalized equation. So here, by using Newton's law of viscosity, that is Newton's law of viscosity is tau is equal to mu into dou u by dou u is the generalized equation. So here we have to take two conditions. So first condition is, this is here we are writing first dy is equal to minus dr. Because y is equal to capital R minus small r, so also we can write dou y is equal to minus dr. So the equation is becoming, first equation is becoming tau is equal to minus mu into dou u by dou r. Now we are comparing the generalized equation, this equation, and with this equation. We are comparing with these both equation. Tau is equal to minus mu into dou u by dou r, that is equal to minus dou p by dou x into r by 2. So I am taking out left hand side because we have to calculate velocity. So here we are deriving a velocity component. So du is equal to taking left hand side, that is equal to minus 1 by 2 mu into dou p by dou x into r into dr. Right, this is the equation we got. So here what I am doing, I am integrating this. To get u, I am integrating this equation, so I got u is equal to minus 1 by 4 mu dot dou p by dou x r square plus c. Right, this is the after integration we are getting, this is the equation after integration we are getting, right, plus c constant. After that we are going with boundary condition. What is that boundary condition? At r is equal to capital R, means at r, this is the small element, this is the small r, this is the small r, and this is the complete capital R. So when this small r becoming the complete capital R, then what happens to the here velocity? That actually we know the velocity is 0, because at the boundaries due to the friction there is a resistance to the flow offered by the boundary by the solid boundary, so that's why the velocity is 0. So at small r is equal to capital R, then the velocity becomes a 0, right? So that condition we are applying in this equation, that 0 here u is equal to 0, minus 1 by 4 mu dou p by dou x into r square plus c, r c is equal to, I am taking c out, I want to calculate c. So c is equal to minus 1 by 4 mu dou p by dou x into r square. So after getting this, I am substituting the c value in the integrated equation. I am substituting here c value, the above c value. Here this c value I am substituting in this equation, velocity equation. I am getting that 1 by 4 mu dot dou p by dou x r square minus, this is the complete c, minus 1 by 4 mu dou p by dou x into r square. So here these 1 by 4 mu and dou p by dou x I can take common, because these both are present in both the values. So I am taking out 1 by 4 mu dot dou p by dou x, right? After that I am getting r square minus small r square, right? here I am taking out minus. That's why actually here minus sign is not there. So 1 minus 4 mu dou p by dou x r square minus r square. So what I am doing, I am taking this minus common. So that's why 1 minus 4 mu dou p by dou x into r square minus small r square. This is the velocity we got, right? So after getting that velocity, we know that the velocity distribution in a circular pipe, that is parabolic, right? So that parabolic. So parabolic means we are seeing maximum at the center. Maximum velocity maximum at the center. So U max is equal to minus 1 by 4 mu into dou p by dou x dot r square, right? Minus 1 by 4 mu into dou p by dou x into r, capital R square. So I want I'm from taking both the equations, the velocity equation, this velocity and U maximum. When I'm taking a common in terms of U max, so what it is becoming, U is equal to, U max is what? U max is minus 1 by 4 mu dot dou p by dou x, right? So that's I'm taking common. So when you take this common U max, so the internal term is becoming 1 minus r by capital R whole square into, that's it, right? U is equal to U max into 1 minus r by capital R whole square. This is the U velocity in terms of U maximum. So from the equation, it is most commonly used velocity distribution for laminar flow through circular pipe. This equation is most commonly used because two velocities are present in this equation. Right now, I need to calculate U average. U average, I got U velocity and also I got U maximum. I want now U average velocity. So to calculate average velocity, here a discharge is coming into picture, right? The discharge is what? Discharge Q is equal to area into velocity, right? So I need a very small discharge which is moving inside the small element, that is dx and dy. In that element, whatever the discharge is moving in this element, that the discharge is dx, written as dx. So here dx is equal to U into pi r into dr is your area, right? So U into 2 pi r into dr. So what is U here? Here already we have given that U max. U max into 1 minus r by half whole square into 2 pi r into dr is your dq, right? So after that, I am integrating this discharge, right, to get U, right? So here I am integrating with respect to 0 to r, radius r, right? If this is the pipe, yes, this is your diameter of the pipe. So here I need only the radius. So I have to take condition 0 to r. So here I am taking 0 to r condition, right? So integrating, that is become U max 1 minus r by capital R whole square into 2 pi r into dr, right? After that, I am taking this common 2 pi U max. This is the constant. So I am taking this out. I am integrating this r by 0 to r into r minus r cube by r square into dr, right? Here this r1 is r. Here it is becoming r cube, right, by r square into dr. So overall you are getting 2 pi U max, 2 pi U max r square by 2 minus r to the power of 4 by 4 r square, right? That is, limits is 0 to capital R. So substituting here in place of small r, capital R, so 2 pi U max into r square by 2 minus r to the power of 4 by 4 r square. So when you cancel these terms, when you do LCM for these, you will get overall pi by 2 U max into r square. 2 pi by 2 U max into R square. You got the discharge here, right? Here, this is the discharge you got 2 by pi by 2 U max into R square. After getting this, substitute. What is that? U average is equal to discharge by area. That is Q is equal to area into velocity, right? So, velocity is equal to Q by A. So, Q already we got pi by 2 U max into R square, by area is pi R square. So, when you cancel these terms, you are getting pi U max by 2. Means that is equal to half of your U max. U average is half of your U maximum, right? And this is showing that U max is nothing but your half of the maximum velocity in a laminar flow through circular pipe. So here U bar is equal to minus 1 by 8 mu into dou P by dou X into R square. So what is the dou P? Here we need to pressure on left hand side. So dou P minus dou P is equal to 8 mu U bar by R square into dx. Here the pressure differences we are taking into picture, that as I said, two sections we are taking, section 1 and section 2, to calculate the pressure difference between these two, P section 1 and section 2. This we are calling P1 and this we are calling P2. So right, sir, dou P. Here is the equation. Dou P is equal to 8 mu U bar by R square into dou X, right? So that I'm taking this dou P on, because calculating pressure drop, dou P is equal to 8 mu U bar by R square integration of x1 x2, because this is the x1 and this complete is your x2 distance from the pipe, right? So P1 minus P2, that is equal to 8 mu U bar by R square, that is x2 minus x1. So overall we are getting that 8 mu U bar L by R square. So 8 mu U bar by R square. This is your delta P, that is equal to 8 mu U bar L by R square. So I need this in terms of diameter. So what I'm doing here, I'm changing this R square to D square. That is, then the delta P is becoming 32 mu U bar L by D square. So this is your pressure drop formula, and this mainly depends upon D is your diameter of the pipe and L is your length of the pipe, and here you need viscosity of the fluid, and also you should know the velocity, average velocity, right? And this equation, the delta P equation, is well known as Huygens-Poiseuille's equation. The laminar flow through circular pipe which we derived is also called as a Huygens-Poiseuille's equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.